physics and engineering, a lot of quantities are represented by vector fields. So let's see what are vector fields. Now here's the precise definition of the vector field in 2 dimensions. So you notice here we got the bold-faced capital F designating our name of our vector field. We have 2 components. The first component representing x values, second component representing y values at any point in the plane. So the idea is we draw graphs like all over the place. So here at the point 1, 0, if we plug a 1 in for x and a 0 in for y into our vector field, we get the vector 0, 1. So here's the vector 0, 1. At another point, such as 2, 1, we would have the vector -1, 2. So we could continue to do this by hand at a number of different points, and that would constitute our vector field. Now the problem is, to actually get a good visualization of this vector field, we need to do lots and lots of points. And so we will obviously be utilizing some technology to help us with that. So here is the same vector field that we just started graphing by hand. However, if we were to use Maple, there's a command called field plot, which looks like this. Now, the way the field plot command works is the first thing we need to specify is our vector field. And notice we're using the vector brackets to designate the vector field. And then we give it the range of values we want for x and y. And then any other options we want. As you can see here, I wanted a nice red color. I wanted to have 10 vectors across and 10 vectors up and down. I wanted to have thin vectors, and I want them to be bolder looking. So again, all of those are options that you can learn about if you just practice with Maple. Now, Maple defaults to drawing arrows, the relative sizes of your vectors. However, many times we do not want the sizes, only the directions. So we can put a parameter in our field plot command called field strength. And if we set that to fixed, we simply get all vectors of the same length. And here are some other vector fields for you to just have a look at. I've drawn here on the left the vector field 0, x. So notice at any point the value is only dependent on x. We have no value depending on y. So we still have components of y that depend on the value of x. It gets a little confusing, but again, that's why we've got technology to draw these for us. And you can see here what the second one looks like. Here's a couple more vector fields of interest to us. These 2 vector fields are called radial vector fields. You can see here the format of a radial vector field has some combination of x's and or y's, and you can see positive means they're all going out from the origin. Negative means they're all coming into the origin. There are modifications to radial vector fields that we encounter quite a bit in science and engineering. If we take the vector field created by the vector x comma y divided by the magnitude of the vector x comma y, we get this, which looks like this. And notice what we've done is created each vector to be unit vectors. Now this is the vector field composed of x comma y divided by the square of the magnitude of x comma y. And so again, that would look like this, which if we put the x squared plus y squared with each component would look like this. We could write that any of those three ways, which means that this is much stronger in the beginning and then tails off quite a bit as you get away from the origin. Very similar to our concept of gravity. Here is the vector field x comma y divided by the magnitude of x comma y cubed. Again, very similar to the previous one, only falls off drastically after you leave the origin. Now, as mentioned earlier, if we multiply by a negative, we just get these going in the opposite direction. Instead of out from the origin, they all go into the origin. Here's another kind of field that we encounter quite a bit in science and engineering. Notice we call this a rotational vector field, and notice the two components, x and y, we have in opposite positions, and one of them is negative. Likewise, we can create modifications of those rotational vector fields by looking at various powers of the magnitude. If we divide by the magnitude to the first power, we just get all unit vectors. If we divide by the magnitude raised to the second power, then again, closer to the origin, the greater the magnitude, and as we move out, the magnitude drops off, which means the size of the vectors gets less. Now when we move to 3 dimensions, this is really where the power of technology comes into play. We can graph a 3-dimensional vector field using Maple just as easily as we can graph a 2-dimensional vector field. Here's an example of a 3-dimensional vector field. And here's the graph in Maple of the 3-dimensional vector field. The real value comes in when we actually sit down with Maple and graph this. We can then take the image and move it around and look at it from various perspectives and understand a little bit more about what's going on with the vector field. Just a static image is not a very good representation of the vector field. But notice how the field plot command is now field plot 3D instead of just field plot. And here's some more, again easy enough to draw in Maple. Notice how the 3-dimensional version of this radial field looks a lot like the 2-dimensional version. All the vectors are emanating from the origin. Now earlier we talked about how we find a gradient vector by doing the partials of some function. So here we've got the function y ln x plus xy squared, which we're going to do the partial of x and the partial of y and write those as a vector. thereby getting the gradient vector for that function. Well, the gradient vector produces a gradient vector field. We can plot that gradient vector field, since it's two-dimensional, using the field plot command in Maple. We've mentioned this word before. For this gradient vector field, the function that we used to come up with that is referred to as the potential function of that gradient field. Now let me show you how this relates to something physical. We're told here that the temperature on a circular metal plate, that means a solid piece of metal shaped like a circle, with a radius of 5, is given by this expression. So we can construct a gradient field from that and draw the graph of our gradient field on the plate. Now again, this is supposed to be conveying a lot of information to us. This is a radial field, T being the temperature. And so what do we see? The temperature is higher around the perimeter of the plate and smaller in the middle. What do we have the temperature doing? The temperature is changing, looks like constantly from outside to inside. Now we've done this before. I've simply overlaid the level curves for T on the vector field. Notice how all of the vectors are perpendicular to the level curves. Finally, if we're given this velocity potential function, we can create the gradient vector field for this by doing the derivatives. So here's the derivatives. A little modification tells us these are what kind of vector field? A rotational vector field. Again, with the x squared plus y squared on bottom, that would be the magnitude squared. We get much larger vectors near the center than we do near the outside. And here I've simply constructed the level curves for the gradient vector field.